Hi, welcome to Real Learning Center. We are going to continue with our heat. We talked about basically fundamentals of heat and then about specific heat and how thermal expansion happens, what is conduction, convection, radiation, all that. And finally, we are going to look at basically state change, where a state of the material changes from one form to the other form and how heat is responsible for that. So let us just basically first get an understanding of what is the meaning of state change. What are the different states? The states of the matter we already know starts from basically solid, and suppose if you basically melt the solid. So what do you get? You get, let us say, liquid. Could be any solid. I'm taking ice here, but it goes from solid to liquid, and that process we call melting. And if you want to go back from melting to solid, we call it basically liquid to solid. We call it as either freezing or we call it as fusion. So we use two words, fusion or freezing. And then from liquid we again go into steam, so from like gas actually. In this case, in the case of water it is steam, and we call that process as evaporation. That is evaporation. And the opposite of that, from gas back to liquid, is what we call condensation. Condensation is the opposite of evaporation, going from gas to liquid. And this is generally what happens. And in some cases, we can see that there is also a possibility that a matter can go from solid to gas directly, which we call sublimation. Okay, so the sublimation also happens depending on the it just bypasses the phase of liquid and goes directly to the gas. So these are our basic terminologies. I'm going to basically concentrate on two things here. One is uh, basically between melting and freezing, and also between evaporation and condensation. So we consider that as a single phase in the sense that uh, the melting and fusion is basically it is two faces of the same coin, in the sense that it is possible that a material can be in the middle of that, part melted, part frozen, and be in that state. And if you supply heat, it goes towards liquid. If you take out the heat, it goes towards the solid. So now, when you look at these things, I'm going to basically do this a little differently, and I ask some questions and see what is our current understanding of these things, and we will check the current understanding with a little more deeper understanding of what these things mean. We kind of know these words and look at what they're understanding. So I'm going to basically ask some questions, and I want you to basically say true or false and check your answer with the final answer and learn if you don't know something. So let's start with very simple thing. Water evaporates only when boiled. This is our experience. Water evaporates only when boiled. Say yes or no. Next, let's go and ask the next question. Steam condenses into water only when cooled. If we cool the steam, then it will condense into water. Yes or no? True or false? Then, when water is boiling, it is necessarily very hot to touch. And when the water is boiling, you can't touch it. You can burn your fingers. True? Our experience looks like true. Let us say true or false. And we also say freezing and boiling always happen at different temperatures. Means boiling, freezing happens when it is going from water to liquid to solid. Boiling happens from liquid to gas. Can it happen at the same temperature? So that's another question, true or false. Then boiling is a cooling process. Do you agree? Yes or no? And then we also have a condensation is a warming process. Condensation means again going from the gaseous state to the liquid state. Is it a warming process or is it a cooling process? And we'll say that it is possible for water to exist in liquid state even at minus 10 degrees centigrade. Is it possible? We know water actually converts itself into ice at 0 degree. Is it possible for it to exist in uh, minus 10 degrees centigrade as water? It's a good question. So let's look at basically answer to some of these questions. So next last statement is, when you heat water, its temperature always rises. True or false? So these questions will be basically answered in this session. So let us say initially I will give answers. Okay, let's check those answers. So my answers are, apart from these three, 5, 6 and 7, all others are false. Only these three are true. So the water exists in Mars even at minus some degrees, yeah, under the ice. It's possible. Okay, so all these things basically we'll discuss and see why the other remaining things are false and only these things are true. So let's start. Let's first of all attack evaporation. So you have seen in somewhere in the field, water completely evaporates and becomes dry. You do go and put your washed clothes outside. All the water within that evaporates. Is the water boiling? No. So what does it mean? It means that evaporation can happen even without boiling. We can say very clearly that water evaporates at all temperatures. Water evaporates in every different temperature, all temperatures. So what does it mean? Then why do we say conversion from water to steam is 100 degrees centigrade? What do we mean by that? So let's look at basically evaporation as a close observation. Look at this. There are air molecules and there are water molecules. And what happens is that these air molecules have certain energy. They go and hit at the surface of the water and get some water molecules up there. And those water molecules will get into the air and roam around. And they may even come back and settle again. So the process of this getting up from here and going there is actually evaporation. Coming back and settling is actually condensation. So if you look at this, it is evaporating all the time from the surface of the water. It is all the time evaporating from the surface of the water. But that's not what we call boiling. We call something as boiling. It evaporates from the middle of the water, from inside the water. If the temperature is very high or if the pressure is low enough, then from inside the water, it can evaporate. And you can see the bubbles coming out. That is basically evaporation happening from inside the water. That's what we call boiling. So boiling is similar to evaporation, where it is converted from water state, liquid state to the gaseous state. However, it is definitely happening from within the water, inside. So that is the difference between boiling and evaporation. Okay, so now let's look at this. Boiling actually happens like this. You can see evaporation from the top molecules, boiling happening from everywhere. So that is basically the difference between boiling and evaporation. So boiling can be done in two ways. So one way the boiling can be done is the uh, temperature can be increased. Simply increase the temperature, and boiling actually happens. You can see it goes up. There is another way you can do boiling. You don't have to increase the temperature. You can bring down the pressure of the atmosphere. So in whichever bottle you are keeping the water, bring down the pressure using a pump. Suddenly it starts boiling and you can see that. So then the air pressure there is decreased and it starts boiling. So boiling need not be done only in using just increasing the temperature. Both are possible. So what we are saying basically is, for the atmospheric pressure that we know of around us at the sea level, atmospheric pressure is a certain atmosphere. And if you go up, the higher the altitudes, the atmospheric pressure actually keeps decreasing. So on the sea level, it is 100 degrees centigrade. But if you go on the Mount Everest, definitely it is quite low. The water boils at a lower temperature. At the higher altitudes, water boils at very low temperature, like 80 degrees, 85 degrees. And water keeps boiling, but it's not hot enough. and it's evaporating. That is why you can see that people who climb, mountain climbers, they sometimes very difficult. They find it difficult to cook. So cooking requires very high temperatures, and you want water to boil at 100 degrees or even more, so that the cooking can happen. Cooking requires water. And what happens is that at higher altitudes in Himalayas, you can see that the cooking is difficult because the water doesn't reach the temperature before that it starts actually operating. So the people, mountaineers generally have this experience. Now let's look at condensation. Condensation is actually, you can see, the water goes up, vaporizes, and again condenses back all that time. So in the sense that like vaporization, condensation of steam into water also happens at all temperatures, need not be at one temperature. Plus, all the time water will be vaporizing and steam will be condensing at every point in time. Okay, all the time. So you keep some water somewhere. I mean, you can see that when you keep some water in a vessel and close the top of the vessel with another plate, and you open the plate after a few minutes and see on the bottom of the plate you can see the droplets of water, which are actually evaporated and condensed. So it happens at all temperatures. We all have this experience. So, but however, we have seen what is condensation and what is evaporation. Do these processes need energy? It's a question. So, the evaporation and condensation, do these both of them, they require energy. So let's look at this. When water evaporates, it takes energy from the surroundings. So whichever the surroundings, if you are supplying the energy, it takes from that. Wherever the surroundings is there, it takes energy when it evaporates. So what does it mean? It means surroundings actually lose energy, lose heat, and hence we can say it is a surrounding area cools down when something evaporates. So it is a cooling process. Evaporation is a cooling process because it cools down the surrounding whenever it absorbs energy. Why does it absorb energy? Because in the steam form, the gaseous form, the molecules are moving with higher kinetic energy. It needs more energy to be in the gaseous form. To be in the liquid form, it needs certain amount of energy for molecules to move around. To be in a solid form, it requires even less amount of energy. So to go from solid to liquid, you need to give it energy. To go from liquid to gaseous state, you need to give it energy. And that energy is sucked from the surroundings. And surroundings cool down. And similarly, when the steam condenses, it gives out energy to the surroundings. And hence, condensation is actually a warm up. If you have burned your fingers in steam, you understand this. So when you are cooking, if the steam comes and hits your hands very near to the vessel, suddenly you feel that it really burns much more than touching the vessel, because the moment steam sits on your hand, it condenses. When it condenses, it gives out heat to your hand. So that is why you feel burnt. So condensation is basically a warming up, heating up process. So now you see, we have said that the boiling is a cooling process and condensation is a warming. Boiling is a form of evaporation. It's a cooling process and condensation is a warming process. So now you understand what we mean. So now let's look at latent heat, a concept called latent heat of vaporization. So what does it mean? It means basically vaporization needs heat energy. So to convert from a liquid to heat, you need some energy. So you have to supply that heat, amount of heat that is basically supplied to convert 1 kg of water into steam is called latent heat of vaporization. For water, it is basically 2300 kilojoules per kg. So that much of heat you have to supply to be able to convert 1 kg of water into steam. So this is basically called as latent heat of vaporization. Now, when water is boiling at 100 degrees centigrade, you take water in a vessel and start boiling. When it is at 100 degrees centigrade, if you give more and more heat, it will not become 101 degrees, 102 degrees, 103 degrees. No. But below 100, it happens. When it is at 30 degrees, you give it heat, it becomes 35 degrees, 40 degrees, 45 degrees, 50 degrees. You can see it, the thermometer, and see it. Whereas when it reaches 100 degrees, even if you keep on boiling, supplying more and more heat, it stops basically increasing. The temperature remains at 100 degrees. That is because whatever heat you are giving is now going to convert the water into gas, which means it increases the kinetic energy of the molecules so that they really come out and become gas. So water at 100 degrees centigrade gets converted into steam at 100 degrees centigrade. Steam is also at 100 degrees centigrade. So till the whole of the conversion takes place, full water, whatever you have put in the vessel, gets converted into steam. Neither the steam nor the water temperature, any of these two will not increase in temperature. So that is basically why when conversion state change is going on, state is changing from liquid to vapor, and then temperature remains constant whole throughout. So this basically uh, is the same case when steam actually condenses, and steam condenses back to water. Whatever energy it has taken to go from water to steam, same amount of energy it gives out to the surroundings, or you suck the energy out of that, then it becomes water. So this is latent heat because in the form when it is in the form of steam, it holds that much heat within it. Latent means one which is inside hiding. The heat that is hiding inside the steam will get released if you convert that into water, and the heat that is hidden inside the water will get released when you convert that water into ice. So that is called latent heat of vaporization when you are doing it from water to steam. So condensation in the atmosphere we will see. Okay. In the atmosphere, a lot of condensation happens. You can see that's how the cloud gets formed. What happens really? So in the atmosphere, what happens is that warm air. So let's look at each one of these words and try to understand that. Warm air rises. Why warm air rises? Because warm air is lighter than the cold air, and warm air rises. Okay. When it rises, it expands. Why does it expand? It expands because in at a higher altitude the pressure is less than the lower altitude. Hence it expands. And when it expands, it cools, it chills. When it is expanding, if you increase the volume quickly, the temperature, volume and temperature are basically inversely proportional. So it chills, it cools down. And as the air chills, the vapor molecules are slowed down. What is the meaning of cooling down? Cooling down simply means molecules are slowing down. Whatever the molecules are going like this, they become slow down. That is called cooling. Cooling simply means that. So when these molecules cool down, or that means it is slow down. So lower speed molecules, when they hit each other, they stick to each other when they collide. Higher speed molecules, when they collide, they rebound and go. Lower speed molecules, when they collide, they stick to each other. And not only that, if there are slower moving other particles in the air, the water condenses on these particles. And when they stick and condense together many particles, it becomes water. So it condenses on these particles. So when that happens, we say that the cloud has formed. So cloud is similar to that. Cloud is just same as that. When water molecules actually condense and small droplets form, and that is what we call cloud, very small droplets. So now you can see that sometimes cloud happens on the surface itself. That means on the ground. Can cloud happen on the ground? Yes. When there is a lot of pollution, a lot of dust particles, then what happens? Very minute particles when they are there, then on the surface of the ground, on the ground itself, they condense, and it's called as fog. You must have heard many times flight would not land because of the fog. That is because the cloud which should have formed there has formed on the surface, on the ground. That is what we see condensation playing in the real world. Now, let's basically look at melting and freezing. The melting and freezing happen at the point between water and liquid and solid. So what happens while melting and freezing? So you can see very clearly the liquid actually gets converted into solid, or the solid gets converted into liquid. So that is our melting and freezing, just opposite of each other, like condensation and evaporation. Now, liquid water, you see, for example, in the case of water and ice, liquid water and solid water, this ice, have different kind of structures. Liquid water, you can see water molecules are randomly attached to each other. In a solid ice, you can see that they have a nice hexagonal structure. Yeah, that is the difference between water and ice, and hence, what happens is that ice actually occupies a little more space than water because they are nicely structured like hexagonal structures. So, if you want to basically see water and ice, you can see the water is just moving around like that, and the ice you can see is basically some structure like this. There is a lot of kinetic energy in water when compared to ice. Ice basically molecules are only vibrating. In water they are actually moving around. So water has higher amount of energy. Melting needs the material to go from, what is the meaning of melting? The material to go from low kinetic energy to high kinetic energy. To go from low kinetic energy and high kinetic energy, we have to supply to that. Whereas on the other hand, when you are going from basically water to solid or ice, you have to move from higher kinetic energy to lower kinetic energy. So you need to basically, it releases energy while doing so. So that is basically the basic funda of melting and freezing. So you can see that when water actually freezes, it also increases volume fundamentally because it now takes more area when you talk about the structure of the ice. So more volume it consumes. So that is, you must have seen about anomalous expansion of water in the previous video. So latent heat diffusion actually is defined simply as the amount of heat required to basically convert 1 kg of ice into water, and it is somewhere around 330 kilojoules. If you supply 330 kilojoules of energy, then you can convert 1 kg of ice into liquid water. The same amount of energy is actually released when water converted back to ice. We have to suck out that much of energy. And when ice is melting at 0 degrees, when you are even more heat, even if you give heat a little bit, keep on giving the heat, its temperature will not rise because there is a state change happening. When state change happening, all the energy that you give is basically used to convert from one state to the other. So the water and ice, both of them are at 0 degree. So if you have an ice water, it's always 0 degree because now ice is getting converted into water. So all the energy you give at that time is used to basically increase the kinetic energy of the molecules to make it water. Then ice at 0 degree gets converted into actually water at 0 degrees. Then you give more energy, then basically start getting heated up. Now let us look at till all the ice gets converted into water, the temperature remains at 0 degrees. So if you look at melting point also depends on pressure. Okay, it's not just always depend only on temperature. So if more pressure is applied, then the melting point reduces. So a very interesting experiment on that is you take an ice cube, a big ice slab. Okay, on that slab, you see, we have put a thread around that, and for those two threads, we have put weight. Now you know what happens is exactly at the point at which this thread is there, the top thread, you can see that it is basically applying a lot of force onto the ice, and that area, that just one line below that thread, the water molecules there are experiencing very high very high pressure. They have pressure per unit, force per unit area expression. That pressure changes its melting point. and whatever energy is around there is sufficient for it to melt. The moment it melts, the thread goes down. So when the thread goes down, we can see that on the top of the thread, the water does not have any more pressure, because it is already thread has gone down. So it quickly fuses, its melting point again changes and fuses back to ice. So thread has gone inside and it is still there. So it gradually, thread keeps going down and falls off without cutting the ice at all. And you can see that experimentally in this uh, picture. So where the thread is going down the ice without actually uh, really cutting it, slowly going down. You can see slowly going down, and the thread finally comes out on the other side, and the ice slab remains as is. So this process of ice doing like this is called as the regulation of ice, where the ice remains as is, and just because of the melting point changes temporarily, the, the thread goes into it. That's called regulation of ice. We use it in another place when doing ice skating. When you are doing ice skating, because of our weight just below the shoes, ice shoes basically, you can see that the water gets converted, the ice gets converted into water, and you start skidding because of that. And the moment you go a little further, that area becomes ice again. So you can keep on skating like that. So regulation of water is basically ice basically happens in ice skating. Now, how to use latent heat and specific heat? So latent heat and specific heat together. So specific heat you already know. A specific heat is a scenario where you can actually, when you increase the temperature of water or anything, how much heat you need to supply to increase the temperature by 1 degree for 1 gram or 1 kg of water. So that is specific heat. So now, if you are given all the three, let us say latent heat of fusion of water, they have given it as 80 calories. Now we are using another unit called calories. We'll talk about that. 80 calories per gram, and latent heat of vaporization is 540 calories per gram, and specific heat of water is 1 calorie per gram. So if you give 1 calorie of heat to 1 gram of water, it increases by 1 degree centigrade. That is basically what is given here. Now, question that is asked is, find the amount of heat in calories required to convert 1 kg of water from 0 degree centigrade ice to 0 degree centigrade water. How much it is? 1 kg of 0 degree centigrade water to 100 degree centigrade water, and 1 kg of 100 degree centigrade water into 100 degree centigrade steam. So each step basically you can calculate. Or you can be asked saying that 1 kg of 0 degree centigrade ice to 100 degree centigrade water, the whole of that, how much energy is required? So for such questions, we need to understand the story of water a little better. So the complete story of water is this. In the earlier sessions, we talked about the specific heat. In this session, we talked about the latent heat, and I am now combining both of them to tell you the complete story of water. So, what really happens? So, let us say the y-axis is basically the temperature. You measure the temperature, and the x-axis is the heat that you supply. So, I keep on supplying heat, starting from ice. I have ice at minus 20 degrees centigrade. So, see here that is basically the yellow ball. That is that is not ice. That is actually showing a point that I have plotted at minus 20 degrees centigrade, the ice. Now I start giving heat. When I start giving heat, what happens is the temperature of the ice starts increasing. So how does it increase? So every degree I want to increase, I have to basically give some amount of energy. That is given by the specific heat of ice. The specific heat of ice says to basically 20 degrees centigrade you want to rise, you can calculate it by using the specific heat of ice. How much temperature it rises? Because specific heat tells you that for 1 degree rise, for 1 unit mass, how much is required. So once you reach 0 degree, you have already reached the top of the ice. So now afterwards, whatever temperature you do, whatever heat you keep, the temperature doesn't rise at all. In the same temperature now, suddenly the state change starts, and that state change is called latent heat of fusion. You use latent heat of fusion. During the state change, that 1 kg of whatever your water, your ice you are given is getting converted into ice, and you use latent heat of fusion for that to calculate. Latent heat of fusion says that per kg or per gram, how much is the energy required. So from there you calculate how much is the total energy required to convert. Now from there, now from at the point B where we are, we have reached a stage where all the ice is getting converted into water. Until then, there is absolutely no temperature that has risen. It has remained at zero, steadfast. Now you give more heat. Now it starts increasing the temperature. So now the temperature again increases as water. And here you use specific heat of water to determine the temperature and determine the energy. And then you reach this point D, where you have actually reached the boiling point, where 100 degrees centigrade. At this point of time, if you give more and more in heat, the temperature is not going to increase, because now it's going to get into converting itself into steam. So water will start converting itself into steam. Now you use latent heat of vaporization to see how much is getting converted, what is the amount of heat required. So you use latent heat of vaporization. So at this point E, actually, now all the water is converted into steam. Now you have actually captured that steam, let us say, in some container, and start heating the steam itself. Now the steam temperature will rise. So it will keep on rising depending on the specific heat of steam itself. So this is the total story of water, how the temperature rises as you keep on giving the heat to it. So in our simple problem, if you see, they have given us only 3 things. That is, we start at B. That means basically we are given 1 kg of ice at 0 degree. We are not going at minus 20. So we start at B, and from B we reach basically C of 1 kg of water is finished. 1 kg of ice becomes water. So that is basically that arrow tells us during that time 1 kg of ice becomes water. So we have to find out how much of energy is required for that. And then that water now gets its temperature rises from 0 degree to 100 degrees. The whole water rises. So we'll use specific heat to calculate that. And then that all that water gets converted to steam. So that during that time we use basically latent heat of vaporization. So these 3 things if we use, we can calculate what we want to calculate. So the first one, the red one, we calculate basically using that. We have been given 80 calories per gram. So we want to find out for 1 kg. Means 1000 grams is 1 kg. So 1000 into 80, which is 80,000 calories is required to convert 1 kg. 80,000 calories, I will write it as 80 kilocalories. Similarly, if you talk about the yellow part where you are increasing the temperature of the water, we have been told that it will actually take 1 calorie per degree centigrade rise in temperature for 1 gram. So now we have 1000 grams, so 1000 into 1, and we have actually not 1 degree but 100 degrees multiplied by 100. So 1001 into 100, 100,000 calories or 100 kilocalories are required to increase the temperature. Now the temperature is all increased, it's all at 100 degrees. Now you're still giving the heat, and it goes into become steam. We are asked to find out what is the energy required to convert all of this into steam. So that is our blue part. So now we have been told that you require about 540 calories are required to convert 1 gram of water into steam. So now we have 1000, so multiplied by 1000. So we will have 540 kilocalories are basically spent in converting all of that to steam. So totally, if you want to ask, is the 540 plus 100 plus 80, totally 720 kilocalories is spent to convert 1 kg of 0 degree centigrade ice to 100 centigrade of steam. So this is how you can do this simple problem. So it can be made complex by giving data. Arithmetic can be made a little difficult, but concept is only this much. So any problem can be done using this simple concept. So one last part in unit conversions we need to know. So 1 calorie is how much joules. So this calorie is a very old concept. Okay, so generally it is defined like this: whatever is the amount of heat required to rise 1 degree centigrade for 1 gram of water is defined as calories. You can see that 1 calorie by per gram. So that is the specific heat of water. Now, 1 calorie per gram per degree centigrade. Okay, so that is the specific heat of water. So if you want to find out that value in joules, okay, that is nothing but 4.184 kilojoules per kg or joules per gram. So we use both are 1000 only, so not a problem. Kilojoules per kg or joules per gram. Kelvin. So that is to get the SI unit instead of degree centigrade. So here you can see basically the table which contains units for all the things: specific heat of ice, latent heat of solution of water. So you may not need to remember all these things. The conversions also may be given in the exams, but sometimes you may not know, so you better to remember some part. So however, one thing that you need to notice is to get the trend right. So you see that latent heat of fusion of water is 330 kilojoules per kg, whereas to the latent heat of vaporization is 2230, is much higher, very, very high. So remember these things. And also it is little difficult to raise the water's temperature than ice's temperature, because ice is 0.5 calories per gram. This is 1 calorie. And it is even easier to raise the temperature of steam. So 0.477 calories per gram. So these are some understanding that you need to have by looking at this. So that is what we have basically understood in the state changes, and we will have some simple questions for you to think over. These are the questions that you have to think about. What happens to the boiling point of water when pressure is increased? Why? So think about it and answer. The second one is: a magician asks you to touch and hold a transparent closed bottle and containing water. The moment you touch it, you hold it, it starts boiling. When you touch the water bottle, it starts boiling. Can you explain the magic using physics? That is an interesting question that you can think about. And where can you withdraw heat? When can you withdraw heat from something without actually lowering its temperature? I take out the heat, but temperature doesn't come down. Can it happen? In what scenario? Think about it. And then, can ice be cooler than 0 degrees centigrade? What is the temperature of the ice and water mixture? Think about this. And then, why will wrapping the bottle in water, or in wet cloth, is actually much more effective in cooling the water than dipping the water in cold water? So this is done by many people. Actually, if you take a bottle, a metallic container, and put water into that and put a wet cloth around it, so very quickly the inside water gets cooled down. So think about why does it happen, based on whatever we have learned today. So these are some of the basic understanding questions. So that brings us to the end of heat. So we completed the heat fundamentals, specific heat and thermal expansion, conduction and convection. Then we talked about radiation in various scenarios, and now state change. So go through this and mull over it and try to solve problems using these fundamentals. Good luck.